Topic that is absolutely critical to the success of modern AI platforms. And I think it is still not discussed enough. Over the next 30 minutes, we'll look at why many AI initiatives struggle to deliver the performance and return on investment that people expect, even after massive investment in GPUs. And as we will see, the answer often has very little to do with models or frameworks. Instead, we'll focus on something more fundamental: how infrastructure is operated, and in particular, how bare metal is managed. My name is David Beamonte. I'm the product manager for MAAS at Canonical, and I'll be your host for this session. Let me start with a simple observation. For many years, progress in AI was driven primarily by better models, better algorithms, and better frameworks. And of course, that innovation continues. But for most organizations today, that's no longer the limiting factor. What we are increasingly seeing is that AI performance is constrained by infrastructure availability, specifically GPU availability. If GPUs aren't available, training stops, inference queues back, and SLAs slip. In other words, the primary bottleneck has moved down the stack. To understand why this matters, we need to be very clear about where the investment actually goes. In modern AI platforms, GPUs dominate infrastructure costs. By most industry estimates, between 70 and 80% of the capital investment in an AI data center is dedicated to GPUs, not networking, not storage, not software licenses. So when the majority of your investment is concentrated in a single class of assets, even the small inefficiencies become very expensive. And that brings us to the second point. AI output depends on availability, not just capacity. There is a common instinct in the industry to focus on raw performance, newer chips, faster interconnects, higher flops. But in practice, availability matters far more than peak capacity. A GPU that it is theoretically very powerful but unavailable due to failures produces exactly zero AI output. In fact, reports show that improving hardware availability by even 10% often delivers a higher return on investment than increasing raw chip performance by 50%, which leads to the third return on investment. The rapid growth of the AI ops market, which is growing at over 30% annually and projected to reach more than $14 billion in the next couple of years, is a direct signal from the enterprise market. So organizations are realizing that success is not only about models and AI data, but also about operational efficiency. So what these dynamics reveal is a shift that many organizations haven't fully internalized yet. Model architectures, frameworks, and best practices are increasingly commoditized. They are mature, widely available, and fast-moving, but no longer the primary constraint. Today, the practical limits of AI platforms are defined by GPU availability and reliability. Every hour of lost GPU time reduces training throughput, delays inference, and limits AI output and revenue. So once you see that shift clearly, it becomes obvious that infrastructure operations now play a central role in AI success. And all this becomes more important when scale grows, for instance, in AI factories. But what is an AI factory? The name, can be misleading. Okay, so this isn't a factory run by robots, as we all know. It's something more specific. It's an industrial scale infrastructure designed to continuously produce, train, and deploy AI models. An AI factory is a continuous capital-intensive production system. GPUs are the machinery, models and pipelines are the production lines, and the output is tokens, predictions, or business decisions. So in that context, utilization is not a nice to have, it is assumed. And every hour a GPU is unavailable is an hour of lost production. So again, availability, reliability, and recovery speed become economic concerns, not just technical ones. And this leads to a problem we see repeatedly. There is often a significant gap between how many GPUs an organization has purchased and how many are actually usable at any given time. Nodes are down, configurations drift, failure take too long to resolve. On paper, capacity looks healthy. In practice, effective capacity is much lower. And this is the key point. Utilization is not just a scheduling problem, it is an operational outcome. So to understand why we need to look at the reality of bare metal at scale. In GPU-dense environments, failures are normal. Hardware faults happen. Drivers break, kernels panic, and firmware drifts. But also thermal and power issues show up. None of these issues are surprising. In fact, they are expected. What matters is not whether failures happen, but how quickly and predictably you can recover from them. This is where many AI platforms quietly lose efficiency. When recovery is manual, everything slows down. Someone has to investigate. Someone has to decide what to do. Someone has to reprovision the node, often differently from last time. So during that entire process, GPUs sit idle. And because these losses are spread across many small incidents, they are often invisible, but collectively, they have a significant impact on availability and cost. And this is actually a topic that we have explored in depth before. A few months ago, we ran a webinar specifically on cost optimization in data centers through bare metal automation with the title Reduce Data Center Costs with Bare Metal Automation. It's available on BrightTalk, and if you're interested in learning more about hidden costs in data centers, please take a look. At this point, people often say, but you're using Kubernetes. And Kubernetes is essential, of course. It does an excellent job orchestrating workloads, but Kubernetes assumes that nodes are healthy. It doesn't fix broken hardware. It doesn't reflash firmware or validate GPUs or redeploy servers from scratch. If the bare metal layer is fragile or slow to recover, then Kubernetes can only work around the problem. It cannot solve it. So if availability and recovery speed define AI performance, the obvious question is, how do we control them? This is where bare metal automation comes in. Bare metal automation is not just about making operations easier. It's about turning physical servers into programmable elastic resources. Servers must be provisioned, tested, recovered, and repurposed quickly and consistently. Additionally, it is important to assume that failures will happen and they are common events. So it's key to handle them fast. Only verified healthy hardware has to be allowed to go into production. So when you operate this way, availability becomes something you can actively manage, not just a matter of luck. Of course, this operating model doesn't happen by accident. Okay, it has to be enforced through automation across the entire hardware lifecycle. It starts with automated discovery, knowing exactly what hardware you have and validating it before use. Deployment and configuration have to be consistent and policy-driven, reducing drift and operational risk. Hardware needs to be consistently validated as part of normal operations. And when failures occur, recovery and repurposing need to follow fast and standardized workflows, not just ad hoc troubleshooting. So these are the non-negotiable features required to achieve a fully programmable infrastructure. This is where MAAS fits in. MAAS is an open source bare metal management platform supported by Canonical. MAAS provides a single source of truth for the inventory and the control plane for bare metal. You can manage physical servers as cloud-like resources, and via the API and the integrations with infrastructure as code and orchestration tools, you can effectively build your own bare metal cloud infrastructure. Let's take a closer look at a couple of important MAAS capabilities. The first one is a requirement that I mentioned earlier, a streamlined lifecycle management. Imagine that a new server arrives in the data center and needs to be added into production. Once it is installed in the rack, it is cabled and powered on, MAAS will discover it as new and add it to the inventory. However, at this point, MAAS doesn't know what kind of server it is. We need information such as the CPU, the amount of memory, GPUs, how many disks it has, and what of what type. Information about the peripherals and the PCI buses, these sort of things. That's something that happens at the commissioning stage. At this stage, the server boots into a lightweight temporary Ubuntu environment, loaded entirely into RAM, leaving no trace after reboot. This is what we call ephemeral. Then it runs a number of hardware and network topology discovery scripts that report the details back to MAAS. The server is powered off, and at that stage, the server is ready. And that means that the server is ready to receive the operating system and the configuration it needs to go to production. So all this lifecycle management is possible because MAAS communicates with the machines directly using an out-of-band channel via the board management controller, the BMC. And what this means in practice is that no human decision is needed to move a server from arrival to production ready. Every step can be automated, it is consistent, and it is auditable. And that directly translates to faster recovery, lower operational overhead, and at the end of the day, more GPU time spent on actual workflows rather than on waiting for someone to provision a node. One of the most appreciated MAAS capabilities is that it can deploy almost any operating system. We are not constrained to Ubuntu, not even to Linux. We can also deploy other Linux distributions, of course, but also Windows or ESXi images too. And that can be done across a wide range of different hardware. Supported hardware can be checked in the list of certified servers on our website. This flexibility removes a common source of friction in large AI environments. One consistent workflow across your entire fleet means fewer exceptions, fewer errors, and faster deployment at every scale. So MAAS offers the ability to use built-in and custom scripts that help verify the integrity of critical components before putting the machine into production. So, for example, testing spans from CPUs, GPUs, and memory to storage and network connectivity. This process ensures that only fully compliant and healthy machines are ever provisioned into production. And this guarantees reliable foundations for the workloads. This is where the availability problems are blocked even before they start happening. So, as we said earlier, a GPU that fails silently in production doesn't just waste compute. It can corrupt training runs, skew inference results, and take hours to be diagnosed. So detecting the problem at commissioning stage costs almost nothing, but catching it in production costs significantly more in time, in GPU hours, and in confidence in the whole infrastructure. And MAAS sits cleanly beneath Kubernetes, which is one of the most popular workload orchestration technologies in AI infrastructure nowadays. MAAS provides the bare metal controller layer, treating physical servers as programmable resources. The two, both Kubernetes and MAAS, are integrated using UU, which enables a full stack orchestration model. MAAS handles, in this case, the bare metal, and Kubernetes handles the workloads. This means that the hardware and workload lifecycles are coordinated. You now have automation spanning the entire infrastructure, ensuring Kubernetes always has a reliable, compliant foundation to build upon. And if you want to learn more about bare metal Kubernetes, we have a white paper called Understanding Bare Metal Kubernetes. Please take a look. At this point, let's explore how these capabilities translate into business outcomes. Here we have some clear examples of how operations impact business. Hardware testing detects faulty GPUs, faulty network interfaces, or other common issues before the machines go into production. And fast fault detection reduces wasted GPU time. Rapid provisioning increases effective capability without buying more hardware. You just make the existing hardware be usable faster. And repurposing lets you adapt infrastructure to changing workloads instead of letting assets sit unused, and so it improves capital efficiency. And consistent deployment and accurate inventory reduce operational risk. They make environments predictable, auditable, and much easier to operate at scale. These are not nice to have improvements. Okay, each one directly affects availability, cost, and return on investment. So when you combine all these capabilities, bare metal automation acts as an economic multiplier. You don't need to change your models, applications, or hardware, but you get more output from the same GPU investment. Less downtime means more training and inference. Faster recovery makes failures less expensive, and fewer incidents reduce operational overhead. So the result is higher utilization, lower cost, and a more predictable AI platform. So to wrap up, here are some key takeaways. First, AI platforms today are limited more by how the infrastructure is operated than by models. Second, GPU return on investment depends on availability, recovery speed, and consistency. Third, Kubernetes is necessary, but not sufficient without an automated and reliable bare metal foundation. And all these can be summarized saying that bare metal automation is now a strategic requirement for AI at scale. So what should you do next? Start by making the problem visible. Identify GPU downtime, reprovisioning delays, and hardware failures, and map them to real business impact. Once you do that, the cost of manual operations become very clear. Then treat bare metal as a first-class layer of your platform, not as something you manage manually, not as something that you manage with different vendor tools. Next, introduce automation by default. Hardware testing, fast recovery, consistent deployment, and repurposing should be part of normal operation. And last but not least, if you are looking for a proven way to do this, evaluate MAAS as the operational foundation for your AI infrastructure. If you are interested, please visit canonical.com/MAAS to learn more about it or start an evaluation. So to close, the message is simple. As AI platforms scale, the limiting factor is no longer models or orchestration layers. It is how efficiently and reliably the underlying hardware is operated. Bare metal automation turns infrastructure availability into a controllable variable. And AI return on investment is not only designed in software, it is also earned in operations. Okay, thank you for joining us today, and we'll now move into the Q&A section, and we look forward to your questions. Okay, so let me check if we have any questions. Just for the new people joining a webinar in BrightTalk, we have, well, there is on the right side of the screen, on the right panel, there is a question mark with a section questions. Okay, so you can go there and ask your questions there. Okay, there is a question. Thank you. No questions for the moment, but we'll consider MAAS. Okay, thank you very much. Can you expand? There is a question. Can you expand more on the automated hardware testing and recovery? Okay, that's a good question. And I think that this is one of the most important features for MAAS. Okay, and probably one of the most ignored ones when you have a data center at scale. I mean, this is something that applies, of course, for AI infrastructure, but I think that it's a more generic issue. So generally speaking, the main issue is that, I mean, when you put something in production, okay, you usually assume that the hardware is going to work properly and it's fine. But as I said earlier, this is something that we cannot take for granted. Okay, so what MAAS incorporates is a set of test scripts. Okay, it's a section that you can where you can incorporate your custom scripts in order to test hardware or to test whatever you want. Okay, but also we have a set of predefined scripts. With these scripts, for instance, you can test, you know, if the hardware is correctly configured, network interfaces, if you want to check connectivity between different devices. I mean, it's up to you. Okay, so it depends on what you want to check. Okay, but that's one of the main issues. And in terms of recovery, I'm not sure if I understand what you mean in the context of hardware testing, but yeah, basically what we do is to identify the tests that have failed. Okay, so that so that the user, well, the system does not put the machine into production. Okay. Okay, another question. Where is the inventory information stored and how is managed, automated and manual? Okay, that's also a very good question. So the MAAS is a platform that uses, this is probably just something internal, but I think it's worth highlighting. So MAAS has its own database. Okay, it's based on PostgreSQL. That's the least important detail, but it's a database that it is distributed. Okay, so that you have, and MAAS also has a high availability. Okay, the region controller and the rack controller. So it stores all the information there. And the point is that MAAS handles and owns the whole inventory information of the whole system. Okay, so you can have multiple racks across the data center. Okay, you have a distributed architecture, but everything is centralized. Okay, so it's so the question is the question about where is the inventory information stored is centralized in MAAS, in the region controller, and in the database, which is highly available and redundant. More questions. There is a question about snaps of Debian. For someone just starting out, would you recommend the snap installation or the Debian packages for a stable production environment? Okay, so there is no straightforward answer. We support both. Okay, so I would be inclined to say that it's better to use snaps. Okay, but it's so if you are starting from scratch, I would definitely recommend that you use snaps. Okay, but it's true that for certain scenarios, I mean, you may be using devs if that fits you better. But our recommendation usually to start from scratch, if you don't have any sort of special requirements, is to start using snaps. As there's another question: as hardware requirement double at alarming rate, how will this keep up in 2-3 years time? Okay, so not sure if I get the question, but I can answer in terms of scalability. Okay, so I think that this is probably the closest to what you're asking. So the point is that MAAS has a scalable architecture. Okay, so this is not something that I touched in the presentation, because I thought that the presentation was much better from a higher level point of view to address the benefits, the business benefits, and the main issues that AI infrastructure and AI factories are facing. But just think that MAAS has a distributed and scalable architecture. We have a central brain, which is called the region controller. The region controller can have multiple instances, okay, so that it is highly available. The same with the rack controller. The rack controller is the controller that is sitting close to the machines, okay, implementing the communication, for instance, such as pixie booting, everything, acting as a DNS forwarder, these sort of things. Okay, so it's DHCP server. So it's getting close to the machines. So if your infrastructure increases, if you need higher requirements in terms of bandwidth or capacity of any kind, it's just a matter of scaling up the architecture so that you have more rack controllers, more region controllers. That's it. So it's super scalable. And there is a similar question. Thank you, very helpful session. How does MAAS handle scaling across hundreds of servers in a data center? This is precisely the same answer. Okay, so MAAS basically has a super flexible and scalable architecture. You can start very simple with a region plus rack controller, just a simple scenario where everything fits in, let me say, in a couple of racks, but you can scale it up to thousands of servers. This is not something unusual. On the contrary, okay, so our customers and standard deployments are measured in terms of thousands of machines. We actually have, and this is something worth highlighting for users who are very interested in super large deployments. We also have another feature or related platform to MAAS, which is called MAAS Site Manager, which is already in beta version. Okay, so that's something that you can check, and we can also distribute the link after the session. MAAS Site Manager basically offers the ability to manage multiple MAAS sites. Okay, so multiple data centers across the globe. Okay, so that's so what I mean is that the scale of MAAS is massive. Okay, at the end of the day, it can span from a couple of servers up to thousands or tens of thousands of devices. Can the PostgreSQL database live in AWS, and would this hybrid cloud architecture provide acceptable MAAS performance? The answer is no. The PostgreSQL database needs to live close to MAAS. Okay, so this is not part of our reference architecture. We've never tested it, and this is not a recommended setup. So the answer is straightforward. I'm not saying that it is not going to work. Okay, so at the end of the day, there is a connection between MAAS and the database, but and that's it. But our standard and recommended architecture does not support that use case. Okay, so I would strongly not recommend using this thing. More questions. Okay. I think I have a couple of additional things. So there, for instance, can I integrate MAAS with Terraform? The answer is yes. MAAS is fully integrated with Terraform. We have a Terraform provider, which is basically a way to integrate MAAS with Terraform. This is basically something that we use constantly with our customers. We deliver MAAS using Terraform. Okay, so this is something, and we configure it also using Terraform. So it's fully integrated. Terraform, I mean, is basically a tool to treat infrastructure as code, which is super helpful. Okay, and along with the orchestration that Juju provides, that's a combination that is super powerful, and we use it extensively, and that's the recommended way of working with MAAS at scale. How is MAAS different from using Pixie-Boolean and scripts or using Ansible? Okay, so this is also a very good question. So Pixie-Boolean is basically a tool. Okay, so sorry, a tool is the mechanism for the deployment of the operating system. Okay, so it's just a mechanism. You need to integrate that in your tooling. The same with, I mean, if you're using Ansible, for instance, or other tools similar to Ansible, you can automate all these things, but you need to do that on your own. Okay, so you can automate the whole system doing your own scripts and your own Ansible scripts and these whole things. And of course, do also Pixie-Boolean. The difference is that MAAS is an integrated platform. So it provides the full mechanism and full lifecycle management. Okay, so it has the full inventory. It controls the machines from power to network configuration, testing, IP address management, all these things. Okay, so you have a single source of truth for the whole data center estate. Okay, and you don't need to be thinking about your scripts to be working, because that's precisely what MAAS handles directly. And of course, it uses Pixie-Boot underneath. Okay, so we use Pixie-Boot in order to deploy the operating system on the machines, but that's just the way we are doing it. And I think that's it. So yeah, I think that we can wrap it here. Thank you very much for joining. I think that if you're interested in learning more, please reach out to us. We will be more than happy to answer your questions. And I would definitely invite you to test MAAS. Okay, it's simple. It's just a 30-minute tutorial that you can run on your computer, and then you will get a grasp of how it works very, very quickly. It's self-contained. You don't need to have any special hardware, just a machine where you can run virtual machines. So thank you very much. Let's wrap it here. Bye.